All right, well, today I'm going to talk about Social Security again. There's going to be one more discussion of Social Security later. I'm going to defer most of my plan until later, but I want to finish the discussion so that we totally understand the subject. It'll also allow me to talk about demography and introduce one of the most famous models in economics called the overlapping generation model. So in the 1940s, someone named Maurice Allais, a French economist, introduced the overlapping generations model into economics. He wrote it in French, and it was sort of rediscovered by Samuelson in the 1950s. I'm not sure whether Samuelson had read Allais. I think Samuelson may well have read Allais. But anyway, Samuelson, so these were 1947, something like that, 1958, in which Samuelson rediscovered it. And you'll see it's a very basic thought, and it seemed at first to challenge everything that we've learned so far. So the idea of the overlapping generations model is that time doesn't have a beginning and an end like we've assumed so far. Time might go on forever. Now, whether or not you believe time, whether there's scientific proof that time goes on forever or scientific proof that the universe has to come to an end, let's face it, many of our institutions presume that time goes on forever. The most important among them is Social Security, which is the most, which we'll see is the easiest thing the model is designed to understand. The idea of Social Security is the pay-as-you-go Social Security. The idea of Francis Perkins was that every young generation was going to give money to the old, but they shouldn't worry so much about it because when they got old, the next young generation would give them money. Obviously, if you thought time was going to come to an end, the last young generation, knowing that they were the last generation, would refuse to give money to the old because they weren't going to get anything back when they were old. But then the second to last generation, knowing that when they got old, they'd get nothing from the last generation's young, they wouldn't give anything either to the old. And working backwards like that, if everybody's rational and it's common knowledge that the world is going to end, nobody would ever participate in the Social Security scheme. So it's clear that there's some thought that the world might end, or at least there's a thought that it's not worth bothering about the world ending. So the overlapping generations model is meant to take that idea extremely seriously and imagine life going on forever. So let's take the simplest example where there's a generation that begins, so generations last when they're young and old. So let's say we're at time 1 here. Okay, and there's a generation that's young and a generation that's old. Maybe I'll write it a little bit lower. Sorry about that. Okay, so there's an old generation and a young generation, and the endowment of the old generation is 1. The young generation has 3 when it's young, 1 when it's old, 3 when it's young, 1 when it's old, 3 when it's young, 1 when it's old. So when you're young, you have 3 apples. When you're old, you have 1 apple. The next generation, when it's young, has 3 apples. When it's old, it has 1 apple, and so on forever. So this will be t equals 1 here, 2 here, 3 here, 4 here, etc. So it goes on forever like that. Now, what did Allais and Samuelson both basically say? They both basically said, look, everybody when they're young is incredibly well off. They're working, they're productive. When they're old and retired and feeble, they don't have very much. But what is it that but what can you do? Where can you trade, according to Samuelson? What does the old have to trade? You know, it doesn't look like there's any trade that can take place. So it seems like it would be very helpful if the old would give the new something, if the young would give the old something, and when they got old, the next generation's young could give them something. So the young could constantly be making gifts to the old. That was Allais and Samuelson's idea, and it's very closely related to Social Security. So Samuelson got a little carried away with his idea, and he said that Social Security was the greatest and only true beneficial Ponzi scheme ever invented. because, you know, in a Ponzi scheme, this has gotten a lot of attention lately thanks to our famous Madoff. So a Ponzi scheme is basically an investment strategy where you take the money that people give you and you buy yachts with it. And then when they ask for their money back, you tell them, well, that you've gotten great returns, and you just hand them money that new people have given you, so they think you've gotten great returns. And when that second generation of people wants their money back, you tell them, well, you've invested it brilliantly, you've gotten great returns, but all you're doing is giving them the money that the third generation is giving you. And you keep going like that until finally you owe so much money you can't find new people fast enough to pay the people off, and then everybody discovers the Ponzi scheme and it all unravels, and the people at the beginning have made out very well, and the people at the end who, you know, the second to last generation, they've lost all their money, and then lawsuits accumulate, and it's quite interesting that in the Ponzi scheme, the very first generations, you know, that benefited are not free, because the whole thing was a scheme, you know, the whole thing, the guy Madoff running it knew from the beginning what was going to happen. And so those first generation of people, there's no reason why they deserve to make their great returns. They benefited from the Ponzi scheme. So the last generations suing Madoff are effectively suing the first people as well. And so we'll see how the courts decide it. But often the people who get out of the Ponzi scheme early still are held liable, and the money's taken back. So we'll see what happens in this case. But anyway, so obviously Ponzi schemes are terrible ideas in general. But Samuelson said, well, when life is going on forever, then there might not have to be an end to the scheme. It just keeps going. This guy gives to this guy gives to this guy. There's no reason for the Ponzi scheme to end if you really think that the world's going to go on forever. And therefore, Social Security is a great Ponzi scheme, which is actually beneficial. So Samuelson even wrote this as a journalist for Newsweek, and there's many. I happened to be a little boy when he was writing this stuff, and I remember some of the articles, and I've gone and found them. And so he describes the benefits of Social Security as a Ponzi scheme. So, you know, this didn't turn out to be quite right, and but it certainly sounds plausible. Another thing he said was that in the Social Security, you know, money you could think of as a Ponzi scheme. Money too, because, you know, you have worthless pieces of paper, you know, but you're willing to hold them when you're young. You'll accept them for goods, because when you get old, you can find the next guy who's willing to give up goods for your money, and that guy's willing to take the money for it, because when he gets old, he can find the next generation's young who's willing to give up goods for his money. So the money, which is a worthless piece of paper, never gets exposed as being worthless, because there's always another generation around to take it who thinks they're going to be able to use it later. So these are fascinating topics that Samuelson discussed, but I don't want to discuss them in this class. I want to discuss Social Security, and so I'm going to do a variant of the model that Samuelson never thought about, which I think is a much more realistic model. So I'm going to do overlapping generations with land. And you'll see that in this model, I'm going to add land to it. It's, I think, a more interesting model, and I'm not going to discuss the paradoxes of infinity, because once you put land, even though time goes on forever, the paradoxes disappear. So rather than spending all the time on the paradoxes and how they come about and do they make sense, I'm just going to add land from the beginning, and it will recapitulate in a nice way almost everything we've done this semester, and there won't be any paradoxes. So what do I mean by land? I mean, suppose that land produces one, so this is land output, produces one every period. So there's another output called apples that just, you know, a tree that's going to live forever, let's call it land, produces one every single period. So here are the periods, you know, and this is what's happening in every period. Okay, now land seems to make the situation much more complicated, but in fact it will turn out that we can analyze this pretty easily. So let me summarize again the model. The model is that every generation Every generation has one agent, or a million identical agents, let's say. Every generation has endowments. So every generation T has endowment. It's generation T, so it's an endowment at time T and at time T plus 1 equal 3, 1. And let's say they all have utility. And the utility of every generation T, which only depends on what they consume when they're young and old, let's say, is log xt plus log xt plus 1. Okay, so everybody cares about consumption when they're young, consumption when they're old. They don't care about consumption any other time. They begin with 3 apples when they're young. They know they're going to have 1 apple when they're old. Everybody's like that for generation T greater than or equal to 1. But generation 0 just has U, so I can call that UT. Generation 0 only cares about consumption when old. And that's that guy at the top. Okay, but I also have to talk about the land. Generation 0 owns the land. Okay, so that's the economy. Very simple economy, but it looks much more complicated than anything we've done before, but it will turn out not to be, but it looks at first glance. So every generation has 3 apples when young, 1 apple when old, except the very first generation, which has land, and that, in addition to, is 1 apple when old, and that land produces 1 apple forever. So we have to figure out what equilibrium is, and then we have to look at Social Security. And by doing this, we're going to understand Social Security much better than we did before. Okay, so any questions about this, what's going on, that I'm going to try and write down what equilibrium is and then solve it, and then we're going to talk about Social Security. Yep? Oh, well, you know, if you only can eat one good, if I put log x1 here, it would be the same thing. Remember, if I take a monotonic transformation, if I double the utility or take the utility e to the utility like that, which is just equal to x1, it describes the same utility. The guy's not trading anything off. There's only one good. So more of the good is better for him. It doesn't matter whether we call it log x or x1. It's the same thing. But that's a good question. Let's call it log x1. Make him symmetric. All right. Well, how would we define equilibrium? So there's financial equilibrium, and then we're going to see if we can solve this. So what's happening in financial equilibrium? Well, it's kind of interesting here. There's going to have to be a price of goods every period, QT. That's the contemporaneous price of apples. There's going to be the price of land every period, pi, let's call it T. So this is apple price. So these are contemporaneous prices. Oh. Okay. With contemporaneous apple price, land price. Okay, what else do we need? Well, we have to decide what everybody's going to consume every period. So generation T, what they're going to consume when young and when old. Okay, and then there's generation 0, what they're going to consume when old. What else do I need to describe equilibrium? That's probably it. And so what's the budget set everybody's going to face? The budget set for T greater than or equal to 1 is the set of all, let's call it young consumption and old consumption. Okay, so that's what you can, so generation T is going to consume something when young and when old, such that what? What's the budget constraint? Well, when they're young, if they want to consume goods, they have to spend QT to consume goods. So this is young, call that Y. Okay, and when they're old, they're going to have to consume, when they're young, they consume that. What else will they want to do? They might want to hold land. So we could call that pi t. And I better add a theta here for their holding of land. Okay, pi t plus theta, that's how much land they hold. Remember how we did this? Okay, and then what have they got? Well, they've got their endowment time t. This is time t, let's say. This is generation t. So their endowment is going to be ETT, but that's 3. So I might as well write ETT just as 3. Okay, and what else have they got? Nothing. Everybody comes into the world with just apples when young and apples with old. So when they're young, they've got 3 apples they can sell. Okay, they can consume something. So 3 minus Q, the stuff they don't consume, they sell, and they can buy land with it. Got all this time, this never happened. Sorry about that. Okay, and then when they're old, what can they do? Well, when they're old at QT plus 1, okay, times Z. Now, are they going to bother to hold the land when they're old? No, because they're going to be dead, and they don't care about their children. All they care about is eating as much as they can. So they're going to sell all their land. So that's got to be less than or equal to what? And so here's the, what are they going to get when they're old? Well, they have QT plus 1. When they're old, and their endowment of 1, plus what? They can sell their land, pi t plus 1, times theta. Whatever they bought the first time, they can now sell when they're old, plus, what else do they have? So one last term. What else is that? So see what they do. Why would you buy land? Well, because when you're young, you're so rich, you don't want to consume everything when you're young. So instead of consuming your whole 3, you consume less. You buy the land because the land's going to be worth something next period. So what is it going to give for you next period? What do you get next period from the land? Well, if you own the land, you get what? You get the dividend, okay? So the dividend, we have to multiply by the price, which on one of the early classes I forgot. And the dividend is 1. That's the dividend. But how many dividends do you get? How many apples? It depends on how much of the land you had. So if you had theta units of the land, you get, if you had 3 acres of land, you get 3 apples, which you can sell for a price QT plus 1. You also still have the 3 acres of land, which you can sell off when you're old. Okay, so that's the revenue you get by selling off the land. And you also sell off some of your endowment, maybe, and that's how you can buy when you're old. So that's what the budget set is of every generation. And the budget set for generation t equals 0 is simply x1 is simply z. We'll call it, z, such that, what does this guy do? Well, Q1Z has to be less than or equal to, what does he have? Q1 times 1, plus he's got all the land. So he's got 1 acre of land. That's all the land there was. So he's got pi times pi 1. He's got all the land. So I've normalized the land to be 1 acre. Okay, so pi 1 times all land. That's what that guy can do. Okay, so equilibrium is xt plus 1 is best for generation t in budget set t, and x1, so this is this and theta. Okay, and x1, did I write theta? Oh, I forgot to write theta in the definition of equilibrium here. So I had to write a theta t. They're also having to keep track of how much land they're going to have. And this is t equals 1 to infinity. Okay, so the equilibrium is, what are the prices every period of apples and land? What does every generation do in terms of their consumption, and how much land they hold, and how much do you consume when you're, how much does that very first generation consume? It's obvious they're going to sell all their land to consume as much as they can. So the budget's set. So x1 solves, so z equals x1, and y z theta equals that, best for generation t in this budget set, and z equals x1 is best for generation 0 in this budget set. Okay, so to say it in words, it's very simple in words, and then we have this mathematics, and it looks complicated, but we're just going to say it's going to be very short to solve it, even though it looks very complicated. So the problem is this. We've got generations who are rich when young, poor when old. There's land that lasts forever. The only way people can save is by holding the land. That's like holding stock. That's holding something real. So when they're young, they're going to take some of their extra endowment, because they're so rich when young, they've got 3 when young, and they're going to use it to buy land. And when they get old, they're going to sell the land and eat the endowment from the land, the dividend from the land, and sell the land, and use that sale proceed to also increase their consumption when old. So they'll be taken care of when they're old because they're able to hold the land. And the question is, how do we solve for this equilibrium? And so why is it, so just to go back to Samuelson and all that, why is it so interesting? Well, one of the reasons it's interesting is that people, when they're young, have to think about the price of land next period when they're old, because they know they're buying the land today, they can see the price today, but when they get old, they have to, why are they buying the land today? Partly for the dividend next period when they're old, but also for the resale value of the land. So everybody is thinking to himself, what's the value of land going to be next period? And of course, the value of land next period depends on what the young in that period are willing to pay. But they're thinking about what they're willing to pay on the basis of what they expect to happen the period after. So everybody has to think about the guy after him and what the guy after him is thinking about what the guy after him is thinking, and it looks very complicated. Okay, and we want to solve for an equilibrium in which everybody can rationally anticipate what the guy in front of him is going to do, which means rationally anticipate what that guy is rationally anticipating the guy in front of him is going to do, and you have to solve for the whole equilibrium and see how it turns out. Okay, any questions about this? It looks very hard, but it's going to turn out to be very, very simple. Yes?
For generation 0, why haven't we added the dividend that he would get from holding the land in the second period?
Okay, because, by the way, I haven't said what happens to the dividend in period 0. So actually, I think that was a good point. So he gets 1. He also gets the dividend in period 0. So I'm glad you asked that question. I had neglected what happened to that. Okay, so to answer your question, remember the convention that we've made, which holds in the market, and it's one of the reasons for the breakdown of the market. One of the reasons why the market seized up in the last year or two is because, or last year, is because when you buy a stock like the land, somebody has to give the money and the other guy has to give back the stock. And the people buying and selling are not actually meeting each other and simultaneously transferring money for the ownership of the land. One guy's in San Francisco and the other guy's in New York, and they're doing it through some screen or something. So the physical asset isn't quite changing hands. So you have to make a convention about, when do you say the deal has actually concluded? So the convention is, that we always use, is that if you buy the land at time 0, you don't get the dividends at time t. If you buy the land at time t, you don't start getting the dividends until time t plus 1. So if the young generation buys the land at time 1, they don't get the dividend until starting at time 2. So the very first dividend at time 1 is going to go to the old guy at time 1, which I had left out here. So the old guy does get a dividend. It's the dividend at time 1 because he began owning the land. So he had it before, so he gets that piece of land. He can even though he's selling the land at time 1, he still gets the dividend at time 1. And the generation that bought it at time 1 doesn't start getting dividends until time 2. So that was an excellent question. It was an oversight of mine, so exactly right. Okay, and that's how it happens in real life. Of course, you know, the length of time might be 3 days, or it might be 1 month, or depends on the security, what the settlement rules are. But there's always got to be a break between when you buy the stuff and when you start getting the dividends, because you know, it just takes time for the whole physical process to happen. So in the settlement for, so they say T plus 3 is a very common kind of settlement, or T plus 1. That means, you know, in 3 days or in 1 day. And so if you're desperate for cash and you have to give, so anyway, I won't get into, we'll come back to this when we talk about the crisis and what happened. But okay, so people who are desperate to get stuff, you know, it doesn't start coming for a little while. So, okay, any other questions? Yes.
Should we multiply that the price of items by Q1?
Should I what?
Multiply what price?
Absolutely. Very good. Okay, any other comments? All right, now how do you solve this? Well, let's figure out how to solve this. So the first thing you can notice is that so Fisher never thought of having infinite time and thought about Social Security, maybe thought about Social Security. I'm not aware that he had any thoughts about Social Security, but he thought, I mean, we didn't have Social Security, so it's unlikely he had been thinking about it. So I don't think he thought about time going on forever. But that doesn't mean his methods aren't, he died, by the way, in 1947, I think, something like that. So right around the time Allais wrote his paper. So what is it that he said all his lessons are going to hold true? The first thing he said is that, look, in every period there's a queue, there are queues on every side of things. Here QT, you know, QT plus 1, QT plus 1, QT plus 1. So if you just double, there's no loss in generality by taking all the QTs to be 1. We have no theory of inflation yet because there's no money or anything. So you might as well assume we're measuring everything in terms of apples and take QT to be 1. So without loss of generality, as they say, you know, QT is equal to 1. And of course that means we can divide every equation by QT. So pi t divided by qt would go here, and we'd have a 1 and a 1. We divide this one by qt plus 1. Still, it's an equation. We have z less than or equal to 1 plus pi t plus 1 over qt plus 1 plus 1 times theta. So we just renormalize all the prices. Okay, so renormalize all nominal prices in terms of apples. Okay, so one simplifying thing is we can get rid of, so think of pi t as the price of land in terms of apples. So we just get rid of all the q's here. Just assume that they're 1. And so we have this equation. Okay, and now that means that pi t implies pi t equals price of land at time t in terms of apples at time t. Okay, so that was a normalization we did many times before. We said that, you know, we might as well assume the contemporaneous price. We can't figure out what inflation is, so let's figure that there's no inflation. The price of apples is always 1, and we're going to measure the price of land in terms of apples. So we get the same equation. It now looks a lot simpler. So the q's we don't have to really worry about. We're just worrying about the pi's every period. Okay, so what did Fisher say to do? So we've got to worry about, what did Fisher say to do? What was Whenever you have an economy, a stock market economy like this, what did he say to do? What was his advice? He said, turn it into general equilibrium. How? By doing what? Yep. Okay, so Fisher said, Fisher's lesson, forget about assets by putting their dividends into the endowments. That's his first lesson. Okay, so you see this is a good summary of what we've learned so far. And his second lesson was look at present value prices. Okay, so he says forget all these pies and things like that. Just look at the present value. So we're looking at P1, P2, P3, ... where PT, price at time 0, let's say, or time 1, doesn't matter. Price at time 1 of an apple at time t. So once you knew the present, so the endowment then, I'm not going to write all this, the endowment of all generations 1 and above stays the same, 3, 1, 3, 1, 3, 1, but the endowment of generation 0 is now 1, 1, 1, 1, 1, 1, 1 forever. Okay, and the budget set, everybody's going to have a budget set determined by the P's. Okay, so now we're just one step from solving this. So there's one more thing to notice before we can solve it. So by symmetry, so observe that by symmetry, we can hope to find an equilibrium with PT plus 1 over PT equal P, a constant. Okay, so, every generation is the same. The only relevant price for a generation is the trade-off between the price of goods when they're young and the price of goods when they're old. That's what Fisher said. The veil of the stock market is just a means of transferring wealth between when you're young and when you're old. And really, you should calculate. All these guys have to calculate. If I buy the stock now when I'm young, it's going to cost me a certain amount of money, and I'm going to be able to get a return. So the real rate of return, right, that they're all going to calculate is going to equal, well, they're going to, by putting in pi t dollars today, they get out pi t plus 1 plus the dividend, 1 tomorrow. Right? So tomorrow they're going to get pi t plus 1 plus 1. So for every, if they put in, buy 1 share of stock, it costs them pi t, and tomorrow they get, pi t apples, we're measuring in terms of apples, and in the future they get pi t plus 1 apple in the future. So that's the real rate of return. That's like 1 plus r t. Okay, but we're going to assume that that's a constant, 1 plus r. We're going to guess it's a constant, and that's just 1 over this p that I told you about before. The ratio, pt plus 1, the present value. So this ratio is just the interest rate between time t and time t plus 1. So Fisher says you don't have to think about all the stock market and what the return on the stock market and all that's going to be. Really, you're just trading off, by doing all that calculation, you're figuring out what's the trade-off between time t goods and time t plus 1 goods. In the Fisher economy, you don't look at the stock market. You assume that everybody knows the present value prices, and therefore the trade-off between time t and time t plus 1 goods, and we're going to assume that's a constant. Because the thing's so symmetric, how else could it turn out except a constant? Okay, so now we're ready to solve it. We've done all the tricks, almost, to solve it. So what is equilibrium going to be? So here's equilibrium. It's going to be a very simple equation. At every generation, you're going to have an old and a young. So what is the total supply of goods in every generation? How much goods are there? There's one for the old apple. Right? If you look at any generation, like this one at time 2, there's that one. No, not that one, a little less. The one in the middle, that's the one for the old guy. Then there's the young guy who has 3. Right? And then there's the apple that the land produces. So this is young apples. And this is the dividend of apples. So that's how many apples there are in the economy. So who's going to be eating them? Well, there's going to be an old guy eating apples, and there's going to be a young guy eating apples. So how much is the old guy going to eat? Well, the old guy is going to spend half his money, and how much money does he have? Well, from his point of view, he's just trading off when he's young against when he's old. So from his point of view, he's got 3 apples when he's young, plus 1 apple when he's old, but that's worth, to him, the trade-off between apples when he's young and when he's old is just given by P. Okay, divided by P. All right, so this is the whole trick. Okay, so we have to spend a minute, so this dawns on you why this is true. And now what's the young going to do? The young generation, what's their income? Well, they only care about the trade-off between prices when they're young and when they're old. Okay, so when they're young and when they're old, they don't care about land, according to Fisher. They don't have to think about that. They just have to know the price, which we're assuming is P for everybody, the trade-off between young apples, which are worth more than old apples. So old, okay, so to them, they have the same income, 3 plus 1 P. Okay, now these P's refer to different time periods, but we're assuming the same. Here's the young. This is the young. Okay, this is the young. So this is divided by 1. So this is the young, and this is the old. And once I solve this equation, we'll have the whole equilibrium. But we need to understand this equation. So where did I get this equation? Okay, so let's take any time period 2, like t equals 2, for example. We know the total apples around that can be eaten are 5. That's on the right-hand side. The old guy's apple, the young guy's 3 apples, and the land producing 1 apple. 5 apples in all. Now, who's going to be eating the apples? They're going to be old guys, and they're going to be young guys eating apples. So the old will be the generation 1 guys. They're going to be eating apples. And then the generation 2 guys are going to be eating apples. Now, the generation 2 people, they've got 3 apples at time 2. So they're looking at 3. But they've got expectations in their head. They're going to think ahead. What's the price of stock market today versus tomorrow? Fisher says, okay, they do all that thinking. They realize the trade-off between consumption at time t when they're young and consumption when time t plus when they're old. That's given by the price p. We've assumed there's a price p. So they're going to say to themselves, okay, I've got 3 apples when I'm young. 1 apple when I'm old is not worth the same. In present value terms, it's just 3 plus 1p, because the old apple's not worth as much at time t as it is at time t plus 1. It's 3 plus 1p. I'm going to spend half of my income, and the price when I'm young, I've assumed that's 1. Okay, so that's what the young are doing. The old guys, now the old guys, what they're doing at time t depended on what they did when they were young. But when they were young at time 1, they knew there was a trade-off between time 1 and time 2 apples. But we've assumed it's the same price trade-off. So we've assumed it's the same P. And so they did the same calculation. When they were young, they were going to spend half their money. This time 1 generation is going to spend half its money when it's young, half its present value when young, okay, divided by, so when they were young, they were going to do that. When they're old now, they're looking forward to spending half their present value when they're old. And the price of apples when they're old is given by P relative to when they're young. So they're going to spend 1/2 times the present value of their income divided by the present value of the price of the old apple, which is the apple we're talking about, because they're consuming when they're old now. So their consumption plus this consumption equals 5. Now, at least half of you must be baffled. So ask me a question to see if we can get to the bottom of this. That's it. That's the whole equation. As soon as we solve this, we'll figure out all the prices and everything in the whole economy. And so we're at the end. But this requires a little bit of thought. So go ahead.
Shouldn't it be 4 plus 1p because there's a dividend? Or maybe like 3 plus 2p? I mean,
No.
where does the dividend fit in?
Okay, the dividend, that's a good question. The dividend fit in here because, yes, there's a dividend. Here's the dividend that got produced, so there's an apple to be eaten from the dividend. Okay, right? Now you're saying, so it's a very important question you're asking. So it's correct what I wrote, but it doesn't sound correct. So what he's saying, the question is, what happened to the dividend? This guy, this generation, say, this young generation, either one, say the old generation, when they were young at time 1, they bought land looking forward to their old age. They sold the land and they got the dividend. How come that's not factoring in to their demand? That's his question, right? Okay, the answer is because that's precisely the point of what Fisher did. Fisher said, yes, in the real world, everybody is thinking to themselves, like Generation 1, I'm young now, I'm buying the land because when I get old, I'll be able to resell it and I'll also get the dividend. But Fisher has thought ahead. Fisher's saying, okay, the guy's going to think about pi t plus 1, that's what he'll be able to sell the land for, and he's going to think about the dividend he's going to get, okay, and his rate of return is therefore divided by how much he had to pay for the land today. That's his rate of return. But see, the top thing is the bottom thing is how many apples he had to give up. Pi t there is how many apples he had to give up to get the land. The numerator is how many apples he gets next period after selling the land and taking the dividend. So that ratio is the trade-off between apples today and apples in the future for him. So if he says to himself what Fisher says, the only thing the guy cares about is that ratio, that trade-off, which we're calling P, 1 over P. That's the trade-off he's going to have in his mind, okay? And so what is his income? This guy began with no land. You know, only 0 began with the land. Everybody else buys the land only as a means of getting to more consumption when they're old. So the whole point of Fisher's insight is you don't have to keep track of how the guy's managing to get the payoff when he's old. All he's doing is he's recognizing a trade-off of 1 plus R, or 1 over P, that trade-off between consumption when young and consumption when old. And all he can do is turn his endowment when he's young into more endowment when he's old at that ratio. And it doesn't matter how he does it as long as we have the right ratio. So Fisher says, forget about the assets, just keep track of the present value prices, and these will tell you the ratio of transformation of goods when young to when old, and that's all you need to know to make a decision. It's the whole point of Fisher. It says you don't need to think about the assets. Now, after we get the P's, we'll go back and figure out what the price of land is. Any other questions? Yes?
Can you explain again why the price in the second chart is just 1? Why P is 1 for the other?
Yes, because I'm taking P as the ratio. So P, this P is here. So it says if I had 1 apple at time t, how many apples could I get at time t plus 1? P of them. Because this ratio, so for every apple I have down here, I can get P apples at time t plus 1. So that ratio is the only thing that, so I might as well call, you know, if the ratio of 2 prices is P, it doesn't matter what their levels are. So I might as well think of one of them as 1 and the other one as P. I could think of the first one as 2 and the second one as 2P. That would be the same thing. Right? So if I thought of the first price is 2 and this price is 2P, I'd put a 2 here, a 2 here, and a 2 here, and it wouldn't change anything. So remember, we learned this this is why the lessons of general equilibrium, they seem so obvious, and then you put them in a slightly different context and you realize how clever Fisher was. If you double all the prices, you're not going to change anything. It's the price ratios that matter. So it's the trade-off between apples when young and apples when old that matter. If you assume that trade-off is given by P, you might as well assume that the first guy, for all we care, he might as well assume that he's measuring the prices when he's young in terms of 1 and the prices when he's old in terms of P. Okay, those were very good questions. It's a little confusing, but when we go back to the original equilibrium, it'll be clearer, I think. But so that's the only equation that we have to satisfy. So we can solve that equation now. Any other questions? Okay, let's solve that equation. That equation is, I'm going to multiply by 2p. So I'm going to get 10p on the right-hand side, right? Because if I multiply by 2p, I get 5 times 2p is 10p. On the left-hand side, I'm just going to get 3 plus 1p plus 3p plus p squared. Okay, and so if I multiply, I rearrange, I just get p squared. Uh-oh. My usual problems here. P squared minus 6p plus 3 equals 0. P squared minus 6p plus 3 equals 0. So p equals 6 plus, and I'm using the quadratic formula, which you might have to, which I assume you know, minus b squared minus 4. Okay, so 6 squared minus 4 times 1 times 3 minus 12 over 2, which equals 6 minus the square root of 24 over 2. So the square root of 24 is a little bit less than 5. So this is going to be a little bit more than 1. Sorry, a little bit less than 5. So this will be a little bit more than 1. So the whole thing will be a little bit more than a half. So let's say it's 0.55. Okay, now how did I know? Okay, so here's a crucial step. How did I know when I said 6 plus or minus, why did I take the minus? Because if I had taken 6 plus this, I would have gotten a gigantic, well, let's come back to that, okay? So how did I know to take 6 minus that instead of 6 plus this? So if this is the P, then what are the prices? What are Fisher's prices? We've just solved for equilibrium. And these prices are going to be we call this one 1 maybe, 0.55, 0.55 squared, 0.55 cubed, etc. That's what Fisher says the prices are. Okay, and we can now figure out everybody's consumption. Y and Z, what's Y going to equal? Well, Y is this thing on the right, 1/2 3 plus 1p, so it's 3.55 divided by 2. So that's 1.775. Okay, and what's Z? You should check, I'm going a little fast here for myself. 3.55 divided by 2 is 1.775. So what is Z? It's going to be 1.5 plus, no, it's 3.5. Oh, it's 3.5 divided by 1.1. Okay, P is 0.5. I'm going too fast for you. Aha. P is 0.55, right? I just got P. So if I want to see now, go back to consumption. What's the consumption going to be when you're young? It's going to be, Y is going to be 3 plus 0.55 divided by 2, which equals that. 3 plus 0.55, that's the guy's income, and he consumes 1/2 when he's young, so that's 1.775. And when he's old, he's going to have the same income, so 1.775 divided by P, which is, so it's going to be 1.775 divided by 0.55. Okay. And that, you can see, no, that doesn't look right. Not divided by 1.7, that divided by P, and that's going to be a little bit more than 3. And so, in fact, if you solve it out, it turns out to be 3.225. Okay, did I go too fast there? So I'm just solving, I'm plugging in 0.55 there. So it's 3.55 divided by half, that was that number, 1.775, divided by p, which is 0.55. So you can see it's a little bit more than 3, because 0.55 into 1.7 is, you know, a little bit more than 3. In fact, if you solve it out to some decimal places, it's that. Okay, so we've solved what everybody does. Everybody now, we know what everyone's going to do. The young are going to spend 1.775, are going to consume 1.775, they're going to consume 1.775 here. They have an endowment of 3 apples, they're not going to eat them all. They're going to consume 1.775 of them. Okay, and what are they going to do with the, and then the old at the same time, what are they doing? They're consuming 3.225. But you notice that those things add up to 5. So the consumption when they're young plus the consumption when they're old, okay, so the consumption of this old guy there is 3.225, and you add the consumption of that, yeah, I went too high there, consumption of the young guy just under him is 1.775. The two of them add up to 5. That exactly clears the market. So at time 2, you repeat the same thing at time 3, etc. So, okay, so you see we've already cleared all the markets, except the one at time 1, which looks more complicated, but we've cleared all the markets. Now, what's the price of land going to be? What's the price of land? I don't know where to write that. Let's write it here. What's the price of land? Which is going to be a constant. How do we figure that out? How would Fisher say you figure out the price of land? So the price of land at time 1, say. What would Fisher say? Yep.
Whatever the young guy would pay for it.
That's one way of getting it. Okay, so what's he paying for it?
Whatever he doesn't spend on consumption.
Right. So from this equation, he spent 1.775. His income was 3. So what's left over? What did he spend on land, therefore? So the price of land has to be 1.225. Now, that's not the way Fisher suggested finding out the price of land. What did he say you should do? What's the fundamental theorem?
Present value all the payments.
And what is that? So the land pays 1 apple every period. So it's paying 1 plus 1 times p squared plus 1 times p cubed plus 1 times p to the 4th, right? Because looked at from the point of view of time 1, you get an apple next period relative to the apples today, that's worth p. An apple in 2 periods is worth p squared at time 1 because, you know, an apple at time 1, at time 2 is worth p apples at time 1 and worth p squared apples at time 0. So you just keep doing this, but this is a perpetuity, and so therefore it's equal to yeah, 1 over r, okay, and we didn't, so it's equal to 1 over r, okay, and so what's r? So we know that, so what's r? How do we figure out what r is? So 1 over 1 plus r equals p, right? Equals 0.55. So therefore, 1 plus r equals 1 over 0.55. And r equals 1 over 0.55 minus 1. Okay, and so this is a little less than 2. Minus 1 is going to be like 0.81 or something. Okay, and you take 1 over 0.81 and you get the same number. Okay, so all right, so that's how Fisher, so let's go back. So Fisher solved everything. He said, I mean, the Fisher method solves it all. It says, well, let's worry about time 0, is time 1. We haven't done that. So what happens every period? Every period, like from 2 onwards, the young guy says, aha, I've got 3 apples. What am I going to do with them? He says to himself, well, the price of land is 1.225, so I could, you know, I could eat some of the apples or I could buy some land. And what does he decide to do? He says, let me eat 1.775 1.775 apples and spend the rest of my money buying 1 acre of land. Now, why am I doing that? Because next period, I know the price of land is going to be the same, 1.225, and I'm going to get a dividend of 1. So I'm going to be getting a rate of return, we just calculated, of 81%. At that rate of return of 81%, so this ratio up here, okay, this is another thing. This number is equal to 1.225 plus 1 divided by 1.225. Okay, that's also equal to 1.81. Remember, R we just calculated over here. Where did I do R? R was 81%. That's the same number here, 81%. Okay, so everybody says to himself, given that there's an 81% rate of interest, I'm happy to hold the whole unit of land, because at that rate of interest, I'm just trading off consumption today for consumption when I'm old at the rate that I want to. Okay, and at time 0, the market clears also. So we cleared the market for every time 2 through infinity. Okay, and that was by this equation. That was up here. By picking the right P, we know every market from t equals 2 onwards was clearing. And Fisher would say, by Walras law, we don't have to worry about time 1. That's going to clear as well. And sure enough, it does. You know, it's a little bit different now. It's just the old guy, but the old guy with his land, which is 1.225, plus his dividend of 1, his land, which is worth 1.225, and his dividend of hope I wrote down the right price of land all this time. Oh, that would be bad. Okay, so the old guy, what does he do? He has his 1 apple, plus he has the land, so he's going to consume. The old guy has his. Oh, I see. The old guy. So what happens at time 1? The old guy has his dividend that he had before. Okay, so he's got the dividend of the land because he's owned the land, you know, forever. So he gets the dividend of 1, plus so that's 1, plus he has an endowment of 1, so he's consuming 2 now, plus he sells the land for 1.225. So that all adds up to 3.225. And then if you add the young generations, 1.775, that indeed clears the market at time 1. So the market's going to clear in every single period. Okay, but we only had to solve it for periods 2 and onwards, which were all symmetric, because by Walras law, according to Fisher, once it clears from time 2 onwards, without even bothering to check, we know it would have had to work at time 1. And sure enough, it did. So as I said, let's summarize now what we've done, okay, and then we can start drawing the lessons. So what we did is we started with a complicated model with land and people having to look forward and expect what the price of land was going to be depending on what the next generation wanted to hold, which depended on what they were going to think the generation of that were going to hold, etc. Very complicated stuff. And we saw that to solve it was very simple. You just do the Fisher thing. If everybody's rational, you can always turn everything, you can forget about the assets and the land and turn everything into present value prices and put the endowments, so you forget about all the assets and just put the dividends into people's endowments and look at all the present value prices. Okay, and the present value prices, by symmetry, we're assuming just grow exponentially, decline exponentially. Okay, and then we could solve the one equation and figure out what that price was, the exponential number p that's, you know, to the nth power gives the nth price, nth present value price. So solving for that p, we then cleared the markets. We found out what everyone was going to do when young and when old, and by plugging in now Fisher's formula, the price of every asset is the present value of its dividends, we figured out what the price of land was every period. So we solved for the whole equilibrium, and sure enough, it clears. And in equilibrium, everybody's doing this calculation. If I buy land today, I'm going to get that rate of return on the land, which corresponds to the P. It's going to be 81%. And so everything works out. Okay, so what's this got to do with Social Security? Are there any questions about this? I sense a little bit of puzzlement still. You shouldn't be that far away from understanding it. So let's hear a question. What don't you understand? Just point to an equation you don't understand. Yes, good. Brave of you. Okay, so Fisher says that the way I solved it is I ignored the assets. So I didn't pay attention to what the assets were. I just put the dividends in the endowment. I didn't pay any attention to what people were holding of the assets. Because Fisher says, forget the assets altogether. Just do the present value prices and augment the endowments. And I found the present value prices by getting this factor P, and then it was just P to the n. And I found what everyone was going to consume. That was it as far as Fisher's concerned. But then Fisher says, okay, once we found general equilibrium, we can go back to financial equilibrium and figure out what the price of land is, which is the present value of the dividends, so its price is 1.225, and the step I left out, which you're asking about, you can also figure out what assets everybody's holding. So Fisher's saying, okay, what assets are they holding? Well, the guy, you know, he's consuming 1.775 here. We figured out the price there of 1.225. So it must be that he's holding exactly 1 unit of the asset. And so the asset market is clearing 2. But that's no accident. Fisher's saying, if you clear all the markets doing the present value general equilibrium stuff, and you go back to the financial equilibrium, you're automatically going to be clearing all those markets too. So I left out the step that, you know, once it's because somebody anticipated all that and got me to calculate the price of 1 in a cheating way. He said, assume theta is 1, then figure out how much money you're spending on the asset. What I should have done, so he did that, what I should have done is done Fisher's trick of figuring out the price of the asset, which is 1.225, and then of course we know the guy must have bought 1 asset in order to use up his budget set, but that clears the market for assets. But Fisher knew that was going to happen. It always has to happen. That's the beauty of what he did. Yes? Yes. So the point is, thank you, I'm coming back to exactly that point. So the point is, when you look at the present value of land, it's going to be P plus P squared plus P cubed plus P to the 4th. The present value of land had better be finite. Okay, so in other words, P has to be less than 1. Otherwise, the value of land would be infinite. And it wouldn't make any sense, because in the very first old guy with an infinite amount of land, infinite value of land, would buy more apples than there possibly were in the world. So you know that the interest rate, the real interest rate, has to be positive. If the real interest rate were less than 0, you would have to, and you had some asset that paid a constant dividend forever, that asset would have an infinite value. So the presence of land, which pays a constant asset forever, forces the real rate of interest to be positive. So Samuelson and all his talk of negative real interest rates, it can't really happen if you think that land is going to, land's going to pay some dividend probably forever. So there's going to be a positive real rate of interest. Okay, and so it means in Social Security, if like the young give up 1 and the young give up 1 to get 1 back, when they're old, they're always going to be losing, because there's a positive real rate of interest, and so every generation has to lose. Okay, so we're exactly the point of all, so it's precisely the point. Because of the presence of land, you know that the real rate of interest is going to have to be positive. You know, Fisher never made this argument. He said it's impatience, and, you know, maybe if people are incredibly patient, it could even turn out to be negative. But, or if, you know, if output was bigger next period than it is this period, you could even have a negative rate of interest. But not so when you have land with a constant dividend forever. Then, if the interest rate is constant, it better be positive. Otherwise, the land would have infinite value. Okay, so it's a new argument for a positive rate of interest. You have to have the land has to have a finite value. Okay, any other questions? So when you solve for a couple of these, you're going to do it very easily. Now, I mean, after you've done it a couple times, this will seem very easy to you. I know it seems a little confusing now, but let's just do a couple more thought experiments. Suppose we do Social Security. What will happen with Social Security? How does that work? What does Social Security mean? Well, Social Security means the young give the old something. And until now, we talked about it as if the young could give the old part of their endowment. You know, the young pay taxes, and the taxes get handed over to the old guy. That's pay as you go. And we talked as if it wouldn't change the equilibrium. But we said at the same time that Social Security was the most gigantic program, you know, any government anywhere in the world has ever adopted. So, and it's on the size, you know, the giveaway was on the was bigger than GNP for a year. You know, 17 trillion compared to 14 trillion. So clearly, it's going to have an effect on the interest rate. So we ought to take that into account if we're doing a more careful analysis of Social Security. So what would Social Security do? How would I take into account Social Security? Suppose every young person gave one unit, you know, one apple to the old guy at the same time. How would I figure out what happened in the new equilibrium? How would the economy change? What would I change and solve differently? Well, all I would do is I would change this to a 2. Every young guy now only has 2 apples when he's young because he's given one of them to the old, and the old would have 2. So all the way through here, I would just change all this to 2, 2, 2, 2, 2, 2, 2. Okay, that's what I would do. So that's the change. Then I have to resolve the equilibrium. So how would that change? What would I change in my one equation? Well, the apples in the economy, the young apples, the guys only got 2. But the old apples, the olds got 2, and there's still 1 apple coming from the land. So that's still 5. But now every generation is going to be behaving a little bit differently. They're going to have 2 when they're young and 2 when they're old. This guy will have 2 when he's young and 2 when he's old, and otherwise it's the same thing. So I just resolve for the equilibrium. Okay, and so if I resolve for the equilibrium multiplying by 2p, I'll have 2 plus 2p plus 4p multiplying by 2p. So, no. Sorry, I just confused myself. I multiply by 2p. I've got 2 plus 2p multiplying by 2p. I have 2p here. Okay, plus multiplying by 2p. I have 2p squared here. Hope I'm doing this right. Okay, and I've got 10p on the right, like I had before. So now I've got 2p squared minus 10p, and that's 4p, so it's still 6p, it looks like, plus 2 equals 0. And so p equals 6 plus or minus 36 minus 8 over 4. Okay, and so that, I hope I did that right. I hope you're checking it. Okay, so that turns out to be P is 2.8, no, Social Security. P is 0.38 now. So this equals, now it equals 0.38. Okay, so 6 minus square root of 28. Okay, so that's like, so it's working out pretty much. So, okay, so 0.38 is the new price. Okay, so therefore the interest rate, 1 over 1 plus r, equals 0.38. So what do you think happens to the interest rate? So r now equals, okay, before I write it, you can figure out what it is yourself in a second. Do you think the interest rate went up or down in the new economy? What would Fisher have said? Up. It went way up. Okay, and so it's actually 347%. Okay, so the interest rate went from 81% to no, that can't be right, went to 161%. Okay, so the interest rate went up. So the loss is even worse than it seemed before. Remember, in present value terms, when you're young, you give up 1, and when you're old, you get 1, and so you lose the present value. So the present value of that trade is this plus that over 1 plus R. Well, now that R has gone up, you're losing any more. So Social Security at the current interest rates looks bad for every generation. After you do the Social Security and everybody understands it's happening, it's going to be even worse in terms of present value. Okay, so Social Security hurts. So Social Security, again, everybody is giving something when they're young to the old. So the guy at the very beginning, at the very top, gains a lot. Everybody else, every other generation loses, and you can compute the utility after Social Security compared to before Social Security, and it goes from something like 2.7 to 2.3. So there's a substantial loss for everyone's utility except for the first generation. On the other hand, we rescued the first generation. Now, there are 2 more experiments I'm not going to be able to finish today, but I'm going to mention them. Experiment 1 is, suppose we had more and more children every generation. How would we take that into account? Well, it's very simple to take into account. It's the same thing with the trivial change. You can figure out what happens with more and more generations, with more and more children. Okay, so I'm going to go back to 3.1. This will only take me 1 minute. Sorry about this. I know time's running out, but let me just finish this story. Okay, so if we had more and more children in every generation, so every 30 years, let's say the population doubled, that's not such a high growth rate, per year, you'd have 6 and 2 here. Okay, and then it'd go up to 12 and 4. Okay, and we'd have to, but again, it's all exponentially growing, and the dividends would also be growing. So this would be 2 and 4 and 8 and 16, etc. Okay, but as you'll see in a second, the way, I won't do it this time, next time, you'll see that it's very easy to solve for the new equilibrium. You just put a, you put a double here thing, because the young, there are twice as many young. Okay, you just solve it, and you do the whole thing. And what happens is, Social Security isn't solved, even though Samuelson was, in a way, wrong again. Even though there are 2, even though there are 2 young people for every old person, so every young person only has to give up half an apple. You only have to give up half an apple when you're young. Okay, and when you're old, you still get a whole apple back. Sounds like now you surely should gain, but the point is you don't, because the rate of interest gets higher. And then we're going to have generations that alternate in size. But all these are very easy to solve once you figure this out. So today, on Thursday, you have to solve a problem just like that, so you get the hang of it. Just one problem to do for Thursday.